RBW and VBW confuse many people when they first use a spectrum analyzer. In this video, I'll explain what they really do using a real analyzer, step by step.
We will start from the beginning. I will show you what RBW controls, and what VBW controls. No heavy maths, only practical examples.
Before we change any settings, let's understand the screen. The horizontal axis shows frequency. When we move to the right, the frequency increases. Now I change the center frequency. Watch how the whole spectrum moves.
The vertical axis shows signal power. Higher on the screen means stronger signal. The noise floor around here is minus 95 dBm. And going up to here, to the signal level is around minus 42 dBm.
Left to right is frequency. Up and down is power.
RBW means resolution bandwidth. RBW controls how much frequency detail we can see. Now I increase RBW from 10 kHz to 100 kHz. Then to 300 kHz. To 1 MHz. Let's stop at 3 MHz. When we increase the RBW, the sweep becomes faster, but the signal looks wider. Now I reduce RBW from 3 MHz to 1 MHz to 300 kHz and to 100 kHz, 30 kHz, 10 kHz, 3 kHz, 1 kHz. So the narrower the RBW, the narrower the signal looks like.
RBW controls frequency resolution. You need to play around to find the right value of RBW according to your signal.
Wide RBW is good for overview. Narrow RBW is good when signals are close together. What that means here is, let's put the RBW at 3 MHz You see here the signal almost occupies the whole screen. So if you have two signals close to each other, for example, one at here, another one at here, third one here, then one here, then all this will be shown in as one signal. You wouldn't see the separate. But when you reduce it, for example, you reduce to 100 kilohertz, you will see this signal here, and then just we say there's one here, you will see one here, you also can see another one here, the one here, we all can see. But of course now I only have one signal here transmitting, but if we have multiple signals transmit here, you will see the difference. We'll show this in a real example later. For this signal showing on the screen, many beginners think the signal is unstable. But often, just because the RBW is too wide, let's reduce it. Now it's 10 megahertz. Let's reduce to 1 megahertz. You will see the signal looks much more stable. If we reduce it further to 300 kilohertz, you see the signal is very stable, looks here. Of course, the noise floor is still not so stable, but this one is, we can change it with the VBW later. What is VBW? VBW means video bandwidth. VBW does not change frequency resolution. You see now VBW is 10 megahertz. You look at the signal here. If I change VBW, the signal here will not change. You see, it's not wide or narrow, but only the noise floor looks much more smoother. If the signal is noisy, it will be smoother also. But here, because our signal is stable already, it's clean, it's not noisy, so you wouldn't see much change here, even you change the VBW. See? Now it's VBW only 1 kilohertz. Let's increase to even 10 megahertz. The signal here still looks the same. But here, of course, the noise floor changed a lot.
VBW smooths the trace. Lower VBW makes the trace more stable. VBW affects how the trace looks, not what you can resolve. RBW decides what signals you can separate. VBW decides how smooth the display looks. First, adjust RBW, then adjust the VBW.
Here is the simple rule. Use RBW to separate signals. Reduce it, you can separate the signals. Use VBW to reduce noise. The value is changing. Now VBW 10 kHz looks okay for us. If it's 10 MHz, it's too noisy, especially when your signal itself is not as clean as the signal from the signal generator. Later I show you in a real signal pick up from the air with the antenna. You'll see the difference. So in practice, you usually change the RBW once. You just need to separate the signal. For example, this two, if it's put at 10 MHz, you can't see it. So you change it once, but not one step, maybe few steps, but once. As long as you separate the signal is good enough already. For example, this one, you change it to 3 kHz, you keep it there. Then you may need to change the VBW many times, because if it's too narrow, the sweep is too slow, so you need to get a balance. Let's reduce it. We're still not happy yet. Okay, this is very noisy signal, so we need a narrow RBW. For example, I'm happy at this shape here because I just need to separate these two signals, and then it looks like it's acceptable for me personally. But if you don't like it, you're still not happy, you can still adjust it, reduce it. For example, you need to change it until 10 Hz. You say, now it's okay for me. So this is normally the way you change RBW and VBW.
And then there is one extra point I like to discuss here. If you look at this spectrum here, when the RBW equal to 3 MHz, the noise floor is around minus 70 dBm. And if you reduce the RBW to 300 kHz, then the noise floor becomes minus 80 dBm. If you reduce the RBW further to 30 kHz, the noise floor is around minus 90 dBm. So the relationship between the RBW and the noise floor actually is calculatable. If you reduce the RBW by 10 times, the noise floor will drop 10 dB, because 10 times decimal is 10 dB. So you can see the noise floor and the RBW, the relationship is defined.
Now you know what RBW and VBW do. In the next video, we will use real-time mode to catch short signals. The screen showing here is a real-time spectrum analyzer catching the Wi-Fi and Bluetooth signal here. Next video, we will discuss the details. Thanks for watching.